You're about to listen to a new episode of Audio Signals. Get ready to take a journey into the known, the unknown, and everything in between. Recorded at no specific point in time nor space, ITSPmagazine's co-founders Marco Ciappelli and Sean Martin follow their passion and curiosity as they venture away from the intersection of technology, cybersecurity, and society to discover new stories worth being told. Knowledge is power, now more than ever.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
And here we go again. Matt, do I need to introduce you or you're going to do that yourself? I want to dive right in.
Okay. I can introduce myself, give like the 20-second version. So my name's Matt Williams. I'm a science communicator and writer for Universe Today and Interesting Engineering. And very soon I'll be joining ITSP Magazine, hosting a podcast called Stories from Space.
And I'm very, very excited
20
about
seconds. Thank you. Me too. It's wonderful. Yeah.
I started a little bit different today. I usually get a much more proper introduction, but the reason why I did this, even if it is another Audio Signals, it's still not your podcast, this one, which we will go into more detail as we have this conversation, because this is our third podcast that we do together. We got connected for the first episode for an article that you wrote about the future of education, if I remember well, about 50 years from now. And then we're like, hey, that was fun. And then we figure out that you are a space journalist. You write for a lot of different publications. You're a teacher. So I'm like, hey, come back. And then you came back and we say, hey, let's talk about space and space exploration. So we went to talk about telescopes and how we actually look back in time with the technology of today and the one that it will be coming up soon, and why we do it, which is always the big question about space exploration. People ask why we do that when there is so much things that we need to take care of here on this planet. And we both know there is a strong connection with that. It's about our future. It's very philosophical. It's about research and knowing ourselves and developing technology that we use back here on Earth. So the bottom line is that we figured out there was so many more stories to be told. We planned this episode about exoplanets, which is very exciting. And then, and then you're like, hey, you have so many stories that are coming from space, so why don't you share them? And so very excited about your upcoming podcast here, which we will talk about a little bit more towards the end of this conversation. But why don't we talk about what we were planning to do, exoplanet. What are exoplanet? A cool name, no questions about it, but what are they?
Well, exoplanet is a short form for extrasolar planet, meaning beyond our solar system. And so it refers to any planet that is orbiting beyond the reach of our sun, anything that is not a solar planet. And there has been some controversy as to, that the nomenclature, what defines a planet and so forth. But yeah, for working titles, working purposes, it's any body that's large enough to be spherical and is orbiting another star. We'll leave the rest for the IAU and all of its detractors to iron out over the years, because that issue is not over. I can tell you that much. But and the rate of discovery is something that has absolutely exploded, and it's going to continue to go that way. At present, right now, there are 5,035 confirmed discoveries, but there's an additional 9,000 candidates. So basically, we've spotted 14,000 possible or confirmed exoplanets so far. That number is expected to get into the several tens of thousands and hundreds of thousands in the coming years, and the potential for research from that is going to be astounding too.
Right. Let's talk about that. Let's talk about why. I mean, we assume there is a lot of planets out there. Of course, I'm one of those that don't believe we're at the center of the universe. That's old news, I think. But there are, right? So without need to go there and explain that, why do exoplanets get so much attention, though? I mean, this because there are potential of life as well in this planet.
Well, yeah, that's what we're trying to find out mainly. I mean, if you look at the studies, the literature, and the regular, all the papers that are coming out that have been coming out for so very long now, there's always this sort of tacit, if they're not talking about habitability, it's in the background, you can tell, right? It's like all these discoveries are pointing the way towards finding life beyond our solar system. And yeah, it's like the more discoveries we make in terms of exoplanets, the more likely we are to find it. And with more candidates to study, we're going to be able to refine our abilities to look for all those the telltale signatures of life. Because, of course, that's a very, very difficult thing to do, right? Finding out what conditions are like on a distant planet. But that's something we're getting better at. So there's a lot of excitement that almost any day now, probably going to be several more years, but the near future, we are likely to find the evidence of extraterrestrial life. And whether or not it's going to be intelligent too, that's the brass ring of all this searching, and it's right up there with the search for extraterrestrial intelligence as a discipline, right? Yeah, we hope to be able to find life and prove that life can exist beyond Earth, beyond our solar system, and that the evolutionary pathways have led to intelligence somewhere other than here. Because, of course, it's very encouraging to know that. And, it also helps us, we imagine that, humanity may not make it. Well, good to know there's thinking creatures somewhere else out there. Maybe they'll get it right.
Yeah, I mean, that's for sure. And with all the planets out there, all the galaxy, and how much we can now explore, it seems almost impossible that there isn't been another form of life that is developed somewhere else. But I want to be able to make a connection maybe with the last episode that we recorded together, which was about the James Webb Telescope, and we talk about the Hubble and the different way the telescope do work. They don't all work the same way. They do not explore the universe using the same technology, and how they all eventually come together in a unified study. So I know I'm making it very, very simple for the audience, but can you explain us how this discovery of more and more exoplanets that happen every day is actually due to the fact that now we do have the technology to do that, and before we couldn't really pierce through the universe the way that we do nowadays?
Yeah, absolutely. No, it's. That's one of the main things I wanted to bring up was that it is amazing how things have changed over the past few decades. Because the first case of an exoplanet detection was in 1992, right? Before that, astronomers had there were some indications, some telltale signatures, but they couldn't confirm anything. So back to the early 20th century, astronomers were sort of detecting the way stars moved, it suggested that there might be some planets pulling on them, right? That has become a main technique for finding them. But yeah, the instruments didn't have the sensitivity. They did not have, advanced computer analytics and ways of really cleaning up and adjusting for or correcting for atmospheric interference and stuff like that. And Hubble was a huge game changer that way, because it demonstrated that, you put a telescope in space, even if it's going to have a smaller mirror than one of these big, huge ground-based observatories, it's going to be able to see clearer and farther than ever before. And then Kepler came along, and that was the biggest game changer. And it's, if I recall correctly, it went up 2007, I believe, or 2009. So it immediately began to use a method here. The methodology had to be sort of figured out, tested out. And yeah, Kepler was the workhorse for one of the main methods that astronomers had devised, and that was called the transit method, right? So it would be watching huge fields of the sky and monitoring stars, and basically it was looking for any indication that these stars were periodically dimming in brightness, just even so very slightly. And so then, yeah, once that was determined, it's like, okay, let's zero in on that star. Let's get a closer look at what's called the light curve, because it'll go up and down all the time for various reasons. And it's like, if we can show that there is a periodic dip in brightness and it's consistent, like every 16 days or so, that means that something's passing in front of the star relative to us. And then we can draw from that all kinds of data that will indicate whether or not that's actually a planet doing that. And that was Kepler's the method it was designed for there, and that resulted in thousands of detections. And it's been followed up with TESS, the Transiting Exoplanet Survey Satellite, and James Webb is going to jump in on this too. And ground-based observatories did that as well. It's like, yes, monitor stars by the thousands, look for the dips, and then, yeah, from that you actually can place estimates on how not only are there planets, how close are they orbiting to their sun, how big are they, and from that, for quite a while now, astronomers have then deduced, it's like, well, that planet could be habitable because it orbits close enough to its sun that it's going to be warm, and it's the size suggests that it's rocky like Earth. So that's a good bet, So we got to look there closer when we can.
And Matt, sorry, because I always have in my head when I make connection like to other story, that's when I remember things. So I remember that this is called the Goldilocks zone, right?
Yes.
When the planet, which is not too hot, not too cold, just right, like the soup.
Oh yeah,
in the story.
Yeah, that's exactly it. So that's another tool astronomers have come up with. It's like, given the class of the star, right? It's like your bigger white blue ones have these much bigger, much farther out habitable zones. Suns like our own, which is a G class or yellow dwarf, and ones that are within that range, slightly smaller, slightly bigger, they have good sized habitable zones in a relatively closer in, whereas your red dwarf stars, which are the most common in the universe, like 75 to 80% of all stars, yeah, they've got small ones very close in. So that's how astronomers will sort of place an estimate on whether or not a planet's in the Goldilocks zone. It's like, yes, so this distance to that distance, a planet would be getting enough radiation, enough light that it could be warm enough that liquid water could exist on its surface. It wouldn't get, just completely evaporated off. It wouldn't freeze. And and like I said, you can sort of tell that based on how quickly the planet is orbiting the star.
how fast it's going to go around. It's kind of like if you look at
Yes.
Jupiter, Mars versus, well, Mars is close enough, but versus planet
Mhm.
Earth or Mercury and Venus. I got
Yes.
two directions that I would like to go with you. So one is a little bit more scientific and technological, and another one is, and I know you like to talk about those things too, a little bit more philosophical about life. I'm going to leave that for the next step. Tell
Mhm.
me about the technology, which we kind of mentioned, I think, in the other podcast on how you can find the biosignatures of a planet by the
Oh,
spectrometers of the lights, and because you're just mentioning that with the transit, you only see a shadow. So how do you know what that
yeah.
planet is made of? How do you know if that planet is solid rock and water, or it has the signature for life? Which then
Mhm.
will bring me to the next question that is more philosophical. So let's talk about the
Yeah.
technology we use for that.
Okay. Yeah. Well, so detecting dips in brightness, the transit method, that's just straight up optical telescopes, right? You take
Right.
in the light in the visible wavelength there, and you monitor it very closely for any curvature, any ups and downs in it, and um, but there's also, and this brings up the other methods. There's also spectrometers, right? They will be looking filters on a telescope there that will measure how the light is shifted towards one end of the spectrum or the other, and that's used. Normally, that's used to measure how fast the other galaxies are moving away from us, right? It's like if a light source is moving away, then its light will be shifted towards the red end of the spectrum because the space it has to go through is expanding, so the wavelength gets lengthened. And red is a longer wavelength of light than the other colors. But if it's moving towards you, it gets shortened and it becomes shifted towards the blue end. So scientists determined that this was also a good method for looking for exoplanets. It's like, let's look at these stars, especially faint ones that aren't particularly bright, and the light coming from it. How is it shifting back and forth? Because, as we all know, stars move, right? They move in place. They orbit around the center of the galaxy. Now, if they're moving in place back and forth, you'll see the light shifting to the red end, to the blue end, to the red end, back and forth, and you can tell by how quickly it's doing that, how fast it's moving in place, and you can then discern the fact that there are objects pulling on it. That would be planets. So yeah, on the one hand, having optical telescopes to read the light is a very good way of detecting them and determining what size they are, whereas this other method that's called the radial velocity method, that's very good at determining how massive they are. So that's usually the way that these two methods together, especially, is how astronomers would determine whether or not a planet is rocky. It's like, it's this big, it's this massive, that suggests rock. Whereas it's like, well, it's this big, but and its mass is tremendous, but that would seem that would suggest a gas giant, right? Now, but in terms of what we're coming up to now is the direct imaging method, where we're going to be able to look at these planets directly. And the technology there, you've got your spectrometers, you've got your optical light, you've got your another tool called a coronagraph, which blocks out light, and that will be used to block out the light of a star, so that we can actually see the light shining onto the planets that orbit it. And then when you measure that light with a spectrometer, and again, it tells you how the color of the light is all broken down. And it's like, well, that corresponds to certain chemical signatures. So it's like, there's carbon in the atmosphere. Oh yeah, we can see that here. Light in there. Oxygen. Yep, it's there's little indications there on the light spectrum there, right? Each of these elements corresponds to a different spot on the color spectrum. And so from that, astronomers are able to say, okay, so we've got carbon, we've got oxygen gas, we got nitrogen. That's everything you need for life to exist there. And that's That's what is referred to as biosignatures. But there are others as well. It's like, well, we see methane. That's an organic molecule. It is associated with life, and it's created by decaying matter. That's another biosignature. Ammonia is yet another. And we're getting to the point where we can see those, and it's important to be able to detect light directly from the exoplanet, because that's how you get the chemical signatures. Any other way, it's just no. You really can't get that data except in very rare circumstances, right?
So that brings me to my next question, and it's a little bit more philosophical, because we say we're looking for a signature for life that include carbon and that include the presence of a life that is the one we know, which is us, human, animal on this planet, and how life works on planet Earth. But my question is, could life be assuming a completely different form where maybe you don't need carbon, maybe it lives in methane, maybe it lives in liquid gas, and would that be a lesser life than our life? But I mean, I'm being polemic here, but I'm just saying, should we open our mind a little bit more when we look for this?
Absolutely, yeah. I mean, this you basically summarized everything, the entire conundrum of looking for life out there. And I've heard a lot of people have asked that. It's like, why are we talking about life as we know it? What about life as we don't know it? And it's like, well, you're right, but any complicated question, it's like if you're asking about spiritual truth, it's like, well, long answer yes with an if, a short answer no with a but. Right? Which one do you want? It's like, well, yeah, yes, we should be looking for life as we don't know, and that is actually there's a lot of literature on that says how we could look for life as we don't know it. But that's addressing the main problem. It's like, how do you look for life as you don't know it, right? You wouldn't know what chemical signatures were involved. You wouldn't really know what biological processes and byproducts were involved. So that's the short answer of why we don't look for life as we know it right now, because we don't know what to look for. But the long answer is like, oh yeah, but our scientists are thinking on that one hard. When you're limited to looking for planets in using indirect measures, which has been true for the most part up until recently, then you got to stick to what you know, right? And it's my publisher there, Fraser Kane at University, he's addressed this many times over the years, and he has said, and I quote this so often, we're currently sticking to the low-hanging fruit approach, right? So we're looking for water, we're looking for oxygen, we're looking for carbon dioxide, we're looking for hydrogen, we're looking for all the things that suggest that a planet would be like Earth, because we know that, and we know of only one planet where life exists, and that is Earth. So, and at the same time, though, it's like, yeah, that's a pretty limited frame of reference here. So let's try to expand the scope. What do we know about other chemical domains there? And you're right to mention methane, because right now, astronomers, they really want to get a closer look at Titan, Saturn's largest moon, because it's got all this weird stuff going on. It's got like indications of all this organic molecules and chemistry, and on the surface, it's got a dense atmosphere. And the only moon that actually has a dense atmosphere, and and it's the way methane works on Titan is exactly the same as how water works here on Earth. So this, of course, is challenging a lot of notions. It's like, is it possible life can exist under those kind of conditions there? It's a lot colder, but you substitute one solvent, water, for another, methane. Maybe you could do the same with ammonia. Maybe life could be nitrogen-based, or still carbon-based, but methanogenic. They consume and break down hydrocarbons instead of water and oxygen. And So yeah, we need to investigate that, because if we find that there is microbial life on Titan, then we know that it can't exist. So then we'd be. And as for whether or not these are like lesser life forms, I would say absolutely not. You know, it's possible that complex life can only exist under certain chemical regimes, but we have no way of knowing that right now, and so yeah, I'd say we must be open to the idea that life can take many forms, and complex life could take many forms, because we've got no real reason to suspect otherwise yet. All we know is we're possible. Let's look and see if there's more of that out there. There's got to be, right?
Yeah, I love how you've said that, because in a way, as you're saying all these things, I'm thinking like, it sounds to me that we're looking for, and I like the reference to the lower hanging fruit, because that's what we know. So in a way, I'm thinking we're looking for other human-like form of life out there. See if we can actually, as many sci-fi movies, I'm thinking Contact, for example, where you can communicate with them in whatever form it is, that there is an intelligence out there. So with this, as we get to 25 minutes into the podcast, I think this is a great opportunity and segue to talk about your new show, which is called Stories from Space. And even the one that we just briefly mentioned, these are stories from space, and like a transit, a shadow, a biosignature, weather on other planets, how that works, and the Doppler effect, and how planets, the universe expand or not. I mean, my brain doesn't even think of how many stories are coming from space and how short of a time we have been paying attention, right? I mean, if we look in the 1600 with Galileo and the telescope, but that's when we really started. So really young in a way, but many stories to be heard. So
yeah,
I love the name. I know a little bit already about the kind of conversation you're going to have, but please take this opportunity here to present your vision, to present your show, and make us excited.
Okay. Oh, I'll try.
No pressure.
I can tell you, yeah. Well, I'm excited to do it though too, because in fact, shortly before we made our introductions there. Yeah, I began doing this very thing. It all started in like early 2020, and I felt like, okay, there's a lot I want to say and convey that I don't always get a chance to do in my writing in the written articles I put out, because of course it's a time-consuming process, right? There's a gap between idea or news development and when it gets out there and gets shared, and I don't always get to write about the things I want to, even though I do feel very fortunate that I often do. But there's always so many other issues there, and yeah, there were a lot of there was a lot of anecdotes too that I wanted to share. In fact, one that comes to mind has to do with exoplanets, and that was the story of how Proxima b was discovered. How there was a news embargo against it, but myself and a colleague of mine, we went digging. We went on a big deep dive trying to figure out if there was some real concrete, reason to believe this, right? Because initially it was just mentioned in a paper, and it sounded like it was coming from a source from the Discovery team. It sounded that way, but there was nothing but this anonymous source to go on. And the fact that the European Southern Observatory, who was the research team was apparently from, they said that they'd be making an announcement later in the month. And it's like, ooh, this sounds juicy. So, yeah, well, I won't relate the whole story here, but the fact is we then started doing a little romp, and we got some tacit confirmation that this was absolutely real. And we were so excited, but we couldn't write about it yet. We had to stick to okay, allegedly, somebody said there's a planet next door, and we're just sort of grumbling and twiddling our thumbs, like, come on, make the press release. We need to talk about this. We know things. And in fact, the third episode of my upcoming series is going to be about exoplanets and the study of them and searching for them. But that was especially exciting because that was confirmation of a rocky planet right next door, in cosmic terms anyway, and that it was within the habitable zone of its stars. So it's like the potential for research is tremendous. We could actually send a mission there. It would take a while to get there, but they were already talking about sending a solar or a light sail, breakthrough starshot, to Alpha Centauri to see what's there. It's like, whoa, divert, go to Proxima, right? we know something's there, or can we at least loop around and make a quick pass through that neighborhood, because we now know there are 3 planets there, and so there's that. And beyond that, I'm grateful for the way you bring up the philosophical implications of this stuff, because it's like, yeah, the science is there, and it can often seem inaccessible. But that's what I like to do. I like to try and break it down, because it's like, yeah, if you spend some time, you do your homework, this stuff will make sense to you, because it's by people, for people. It's just people often feel intimidated by it because they don't have the background, and talking to someone who does have a background, they don't always express it in terms that will make sense to the average person on the street. But at the same time, yeah, it's like the implications of every discovery are profound, and that is more than anything what I want to talk about, right? Because it's like,
as you're saying all these things, I think about, and I had conversation. I'm lucky because I love space. I love space exploration. It's not my background, so I'm always the dumbest person in the room, and I love that because I just love to learn. And I've been lucky to sit on podcasts with astronauts, with people from NASA, with professors, with people journalists like yourself, and I just cannot wait. But sometimes there is a limitation of, can I understand this? So I like the concept that you're going to break it down. And the other thing is, from what I understand, then, is that you're going to make it a little bit more human as well, talking about the people that invested their time historically, nowadays, the project, the researcher that studied these things and make possible this discovery. Because again, it's still a very early stage where we are. I mean, you're thinking about, it's relatively close, and I'm kind of laughing because I don't know the number, but it's probably few light years.
Yeah, the nearest star, yeah, it's 4.25 light years.
So
and yeah, it's like,
I'm not going there on my way to the grocery store today.
No.
So tell me about the stories of the humans that you want to tell. I mean,
oh yeah, well, throughout this series, and I've already managed to get a few people on, and managed to interview them over the years. And so when I told them about this podcast, yeah, many of them were excited to come on and share stories. Yeah, these are people who were either the brains behind something, the researchers who were part of a breakthrough, or who went to space, who were part of missions. And given that I've already talked to some of these people about this, I feel comfortable name dropping. But guests that will be appearing in the first season, well, they include Harold Sonny White, who was the NASA researcher who worked on warp field mechanics for NASA. And he's doing that again with a nonprofit organization. They're trying to develop, in a step-by-step kind of way, right, advanced propulsion systems that will eventually lead to faster than light travel. And since 2012, right? 2012, I'd heard about this, how, this guy from NASA looked at the equations, the old Alcubierre equations, and found that they were actually doable. It's like, oh my God, so FTL is theoretically possible? Well, some still disagree with that, but that was the announcement. That was his revelation, and NASA took it seriously. So all throughout, ever since then, I thought, oh my God, I thought the book was closed on that. If that is possible, think of what we could do. Also, Robin Hanson, the guy who coined the whole filter hypothesis idea, and who does a lot of theoretical research about extraterrestrials and advanced extraterrestrials and when we might meet them. He was another. And also, yes, someone who does not need much in the way of introductions there, but Dr. Sian Proctor, who recently went to space as part of the Inspiration-4 mission. She's a very busy woman, but I'm going to get her on the first chance I get there. And she's happy to do that because, of course, this gives people who are so inspired by what they do and who've made a big contribution, right? They get a chance to talk about it to others and share that. That makes their day, right? I mean, it makes my day to have them on, but I've always found it astounding. It's like you guys are happy and excited to be, coming on a show of mine or speaking to me for an article. Yeah. I'm the one who's grateful here, right?
Absolutely. I share that feeling 100%. But it also tells me that people that do this, they do it because of their passion. And their passion is discovery, learning, and of course, sharing that knowledge with other people, which is also what you will be doing and what we aim as an objective with ITSP Magazine, where we say knowledge is power. So we hope to inspire people to go into STEM, to young generation, and for the older generation that maybe they're not going to be astronauts, but they can understand a little bit better why we go to space, why we explore, why we research. So to end this conversation with the tease that once this goes live, the podcast Stories from Space will be live. So there will be notes in this podcast here to jump on the other show, and there'll be a pilot that I already heard it. It's great. So please join the conversation from day one. But I would love for you, Matt, to finish this conversation with an invitation. Who are the people that you would like to listen to your conversations, to your podcast, and what do you hope they get from it?
Well, I would say everyone, really. I would love it if everyone and anyone listened, because it's like, this is definitely what I want, is for this to be a show for everyone, right? You don't need a background to understand what's going on. It is incumbent upon me to make the science make sense. And there will be very brainy people coming on the show, to talk about what they do. I promise that I'm going to be there to be the translator as best I can. What I definitely would love is young people who have an interest in space. Check this out, because I want to talk to you directly. There's a lot of things that that I know you're interested in, because I was too, and I want to speak directly to that, and also tell you the kinds of things that you might not know yet. And older people, adults, seniors, anyone. It's like, if this is something that you've always been interested in, and you love hearing about the new developments in the stories, but of course it's very hard to follow. And who has time to follow the literature and learn what all this stuff means? Very few people. So that's what science communicators are there for, and that's who I want to be to you. I want to be the guy who helps make sense of this to you, because, like you, I'm not a physicist by background. I'm not an astronomer or astrophysicist by background, but I always love this stuff. So it's like, if I can make sense of it to myself, then well, you could too, but you probably don't have the time. So let me do it for you, right?
Yeah. To each one is passion and his job, and to bring it down to an understandable way language that translates to everyone else. So again, Matt, it's an honor that you picked ITSP Magazine for your podcast. I can't wait for us to share it, for people to give us the feedback, ideas for conversations, and I want to invite everyone.
Absolutely, yeah. And I want to alert the potential listeners there. Yeah, our first episode, the kickoff episode, will be about Artemis and going back to the moon, because that is super relevant right now. But, we'll branch out from there. There's no shortage of things I want to talk about, and selecting just like a handful of them for the, first 2 episodes was really hard. But I think I got a good mix.
I think it's a great way to start the conversation, as everybody's talking about it. I mean, I was barely born when we went to the moon for the first time. I don't remember in person, but I was born in January '69. So hey, it was right there, and we're going back. So that's an important things to get started with this conversation. Is a little bit more understandable. The moon is right there. We see it all the time. We've been there before, and so it seems a little bit easier to go back. Although I don't think easy is the word we should ever use when we launch rocket into space. So there's a ton of people doing that job, and they're not the one that goes into the rocket either. But there is a ton that works to make that happen. So maybe we'll talk to those people too. Anyway, once again, this is just a gate to open to these stories from space. And we hope you're going to follow that, and you're also going to keep following Audio Signals, where we'll probably have Matt back again, and other people that are going to share important stories with us. So thank you, everyone, for listening, and share with your friends. I think the conversation are exciting, and we want you to tell everyone else. Thank you, Matt. It was an honor.
Thank you.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
We hope you enjoyed this episode of Audio Signals. If you learned something new and this podcast made you think, then share ITSPmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society, and some even beyond that.